Let's talk about the third way to get the change in enthalpy for a reaction without actually doing it. And it is to use standard average bond dissociation energy values. What bond dissociation energy values do is they allow you to draw Lewis structures for the substances and determine what bonds you are breaking and what bonds you are making. And then you can add up the amount of energy needed to break all the bonds, add up all the energy you get back when you create all the bonds, and we can find the difference, and you can determine the change in enthalpy or heat for the reaction that way. In order to do this, you got to have two things. Okay. Number one, you got to be really good at drawing Lewis structures, right? Which we like just did a week ago. So like you didn't have time to forget yet, right? Right. And you need to be able to remember that breaking bonds requires energy. Breaking bonds requires energy. And creating bonds releases energy. Breaking bonds, you got to put energy in. Creating bonds gives off energy, releases energy to the environment. Okay. Breaking bonds requires energy. Creating bonds releases energy. Okay. If you can remember that, we're going to be all right. Okay. So I hit the wrong button. Here's how it works. Somebody, somewhere, somehow figured out the average amount of energy needed to break all these different types of bonds. So on average, the amount of energy needed to break an H to H bond would be 436 kilojoules of energy. So if I wanted to break a mole of H to H bonds, if I wanted to break 6.022 times 10 to the 23rd H to H bonds, I'd have to put in 436 kilojoules of energy. Also, because of the law of conservation of energy, if I created a mole of H to H bonds, it would release 436 kilojoules per mole of energy. So breaking requires energy, making releases energy. So if I want to break a mole of H to C single bonds, that's going to take 414 kilojoules of energy on average. Key word here is average. We'll talk about the average, what the average means in a moment. A lot of these trends make a whole lot of sense. Obviously, it takes more energy to break a triple bond of a certain type than a double bond of that type than a single bond of that type, right? If I want to break a C to C triple bond, it's going to cost me 837. Breaking a C to C double bond costs me 611. And breaking a C to C single bond is going to cost me 347. I will give you a copy of this table tomorrow when I see you guys for lab, so you can have this if you want to use it to work a homework or something. Here's the thing, though. The big downside to this method is this word average. Okay. This acts like all C to C single bonds are created equal, and they're not. What this table does is essentially it's saying the rest of the molecule doesn't matter. It's just a C to C bond, and that's not true. We know that the rest of the molecule does, in fact, influence the bonds inside the molecule. So, you know, like what's going on to the left and right of this C to C single bond can make that bond stronger than 611. You can make the bond stronger than 347 or kilojoules per mole, or it can make it weaker than 347. These are just average values. Like if you look at the average C to C bond, they looked at a bunch of them, they figured out the amount of how strong they were, and then they averaged it and got 347. So it's just on average the strength of these bonds, but it's not necessarily 100% accurate. How far off can these values be? They can be off by up to about 5%. Okay, they can be off by up to about 5%, which is not great if you really, really want to know the values. However, I will say this. When I did research, I had this table pinned up in my little cubicle, and so did every other synthetic organic chemist. And we didn't really care that it was off by like 5% because I was just looking like, hey, before I did a reaction, I wanted to know, is it going to get hot or is it going to get cold? And is it going to get really hot or is it going to get really cold? Because I got to take precautions, especially if it's going to get really hot. right? I don't want to be mixing the stuff in a flask in my hand, and now it's got an enthalpy of negative 2,800, and I'm going to burn my hand off. Okay, or it's gonna start boiling, and it's gonna boil the acid right out over my hand. So I quickly drew the Lewis structures, which I'll show you here in a moment, and then I would use this table, and within a matter of 2 minutes or so, I could figure out, approximately how exo or endothermic was it going to be. And I didn't care if it was off by 5% or not, because I didn't care about the actual number. I just wanted to know, hey, was it going to be really exothermic or really endothermic? Okay. So a lot of synthetic chemists, we do that, and we synthetic chemists are very good at drawing Lewis structures. So like we could do it like in a jiffy. It's not a real problem. So let me show you how this works. The first thing you have to do is you have to draw the Lewis structures. So I'm actually going to write this guy down on the board. Give me a second. First thing you got to do is draw the Lewis structures. So if you have a periodic table, right, let's go through this. So that's going to be 4 times 2, that's 8, plus 4, that's 12 electrons to work with. Carbon to carbon, we got 2 hydrogens coming off of each. 2, 4, 6, 8, 10. We used up 10. We got 2 left, and we are short 2. So what does that mean? It means you got to add a bond. So we're going to put a bond right there. So there's our first structure. H2 is really easy. 2 electrons. You just connect the 2 H's. How easy was that? And now C2H6. That's 8 plus 6. That's 14. 2 carbons, 6 hydrogens, 2, 4, 6, 8, 10, 12, 14. You got nothing left. So this guy plus this guy goes to this guy. And now what we need to do, what I do, is I make a list of all the stuff that I'm breaking and all the stuff that I'm making. Okay, so here we go. What am I going to be breaking in this molecule? I'm going to be breaking 4 C to H single bonds. So C to H single bonds, I'm going to be breaking 4 of them. We're going to look that up in a second. What else am I going to be breaking? I'm going to be breaking a C to C double bond, and just one of those. And I'm going to be breaking an H to H single bond, just one of those. Cool. And then we're going to come over here, and we're going to say, what are we going to be making? Well, I'm going to be making 6 C to H single bonds. And I'm going to be making 1 C to C single bond. And now what I need to do is I need to go back and find these values. So let's go back to the bond dissociation energy table. So the first thing, we had 4 C to H single bonds. Those are going to be 414. 414. And on the other side, we have the same kind of bond. So I'm going to put that over there. That's 6 times 414. There's a shortcut you can take there. We'll talk about that in a second. We're also going to break a C to C double bond. That's 611. We're going to break an H to H single bond. That's 436. And then, let's see. We already got the C to H. That's 414. The C to C single, 347. Cool. Awesome. So we're going to add these guys all up. We're going to add these guys all up. We're going to get the total amount of energy we're putting in to break these bonds. And we're going to get the total amount of energy we get back that's released when we create the new product bonds. So how much energy do we need to put in to break up the products? So 4 times 414 plus 611 plus 436. That's going to be 2,703 kilojoules of energy needed to break the bonds. Let's figure out how much we get back. We're going to get back 2,831. So this reaction is going to be exothermic because we get more energy back out than we had to put in. How do you get the final answer? Well, to get the change in enthalpy for the reaction, its bonds broken. minus bonds formed when you're using this method. So it's kind of the opposite of the standard enthalpy formation method, which was products minus reactants. This is reactants, bonds broken, minus bonds formed. This is reactants minus products. But I don't like to think of it like that. I just say bonds broken minus bonds formed. So if we get the change in enthalpy for this reaction, the change in enthalpy for this reaction, 2,703 minus 2,831. And we get a negative 128 kilojoules per mole of energy. And again, it's exothermic. You get more energy back out than you had to put in. So negative 128. Awesome. Very good. Let's take a look at another one. Oh, come on. I got to have some more. Well, I'll tell you what. We're just going to make one up. Let's go back and do this reaction right here. And let's compare our answers. Give me a second. So what do we need to do? We got to draw the Lewis structures for everything. So why don't you take a second? That's the first thing you need to do. See if you can draw the Lewis structure for those four things. All right. Let's check those Lewis structures. So we got CH4. That's 4 plus 4. So that's 8. Then we got two O2s. So forget the 2 for a second. That's 12. Then we got 4 plus 12. That's 16. You guys have hopefully drawn carbon dioxide so many times. And then 2 H2Os. Okay, now here's my tip for you. In this reaction, we got coefficients. You can put a 2 here, or you can draw the Lewis structure twice, which is what I tend to recommend so people don't forget. You can actually visually see how many of the bonds are breaking. Okay. So hopefully we drew that. Now we need to kind of tally up everything we're breaking, everything we're making. So we need to break 4 C to H single bonds. We need to break 2 O to O double bonds. We need to create 2 C to O double bonds, but they're in carbon dioxide. We're going to talk about that in a second. We'll put an asterisk there. We'll talk about why. And then we need to create 4 O to H single bonds. Cool. Let's go to the table. The C to H single bonds are going to cost us 414. The O to O double bonds are going to cost us, where are those beasts? They're going to cost us 498. C to O double bond. Take a look. If you look at the C to O double bond, it says 736, but it's got an asterisk. And if you go down here, 799 and CO2. I like to call CO2 the Barry Bonds of bonds. Okay, here's why. I don't know if you know this. Barry Bonds, played for the Pirates and the Giants and hit a whole bunch of home runs, has the most home runs in Major League Baseball history, but he's not in the Hall of Fame because he took a whole lot of steroids. Okay, and if you go to Cooperstown, the person who caught his record-breaking home run ball, they sold it to one of those .com millionaires or billionaires. They bought the ball and then branded an asterisk in it and gave it to the Hall of Fame in Cooperstown, New York. And it's on display there. It's a ball right in the middle in a special case, and it's got an asterisk branded in it. There's a moth in this room. Anyway, they're saying, hey, this dude did break the record, but he didn't do it legit. So we're going to put an asterisk on here. And I like to think of carbon dioxide as the same. These C to O double bonds are on steroids. They're so strong, they're not anywhere close to 736. It's the only asterisk in the whole table. 799 in CO2. So these are actually 2 times 799, right? 2 of them. And then we need to look up that O to H single bond. The O to H single bond going to release 464. when it gets made. 464. Right on. And now we're going to add it up. How much energy we got to put in? How much energy do we get back out when we make them? That would be 2,652 kilojoules of energy to break these reactant bonds. How much do we get back when we make this? 2 times 799 plus 4 times 464. We all get back 3,454. Again, it's going to be exothermic. We're getting more energy out than we put in. Let's subtract 2652 minus 3454. And we get a negative 802. Exact same answer as when we did it with the standard enthalpies of formation. So we said this method can be off by up to 5%, but this time is actually spot on. Negative 802 with both ways. So it's pretty awesome. Okay, that ended up working out like that. Hopefully you got all three methods down now. So it's Hess's law. That's where you can flip reactions, multiply reactions by stuff, and get the change in enthalpy that way. We got the standard enthalpy of formation where you use the values in that appendice, sum of the product standard enthalpy of formations minus the sum of the reactant standard enthalpy of formation. And then we have the average bond dissociation energy method, which uses that table of BDE values, bond dissociation energy values, and Lewis structures, and gives you an approximation within about 5% of the enthalpy for the reaction. So